Yeah, I know, it kind of gets compressed here, but this should be broken up into shells. So what are the shells here? The first shell would be the 1s. And then the second shell would be the 2s and the 2p. So the first shell is filled, the second shell is filled. Third shell would be the 3s and the 3p. So this would be the third. And then in the next shell we have the 4s, the 3d, and the 4p. The 4p are empty here, but we're just going to get in the habit of writing it because we'll just complete the fourth shell. So, well, that looks good. So this was the second exception that you had to memorize. What was the other exception? Chromium. Right. And so here we promoted an electron from the 4s. It should be 4s2, 3d9, but here it's 4s1, 3d10. So that's good. Got that. The other thing that we could do is offset a little bit. One thing I'd like to do, just for writing out the quantum numbers, is to write the L's in different columns. So here we're going to have L equals 0, N equals 1 here. So if N equals 1, L is 1, that's a 1, 0 orbital. It's a 1, 0, and then M, what are the possible M values? The M values are going to range from -0 to +0. Well, -0 to +0 is just 0. So this is a 1, 0, 0 orbital. And then if we go to N equals 2, which would be here, let's say this is the 1s orbital. When we go to the 2s orbital, N equals 2. So that's 2, 0, 0. So this is a 2, 0, 0 orbital. Go to N equals 3, etc. But when N is equal to 1, what are our possible L values? Well, L can be 0. Can L equal 1? That is, when N equals 1, can L equal 1? No, why not? Yeah, N minus 1 is the max. So 1 minus 1 is 0. So 0 is the max. So we are not allowed L equal 1 here. So there's no such thing as a 1p. However, there is such thing as a 2p. So we have the 2p orbitals. And so the way we could read it is N equals 2, L equals 1. So this is a 2, 1 orbital. It's a 2, 1. Well, what are the possible M values? M values are going to range from -1 to +1. So it's going to be -1, 0, and 1. So we have 3 possible M values. So we'll do 2, 1, -1. That's the first possible. Then 2, 1, 0, that's the second. So 2, what I do is just 2, 1, 0. And the last possibility is a 2, 1, 1. It's 2, 1, 1. So those are my 3 2p orbitals. What I'd like to see is just a little bit bigger jump here, but I know there wasn't enough room here. This goes up to the 3s. And then the 3s is what? Well, N equals 3, L equals 0, M equals 0. So this is a 3, 0, 0. If N equals 3, then we're allowed L equals 0. We're allowed L equals 1 here. And so we'll have a 3, 1 that's allowed. 3, 1, -1. We go 3, 1, 0, and a 3, 1, 1. So those are my 3 P's. But, so we're allowed L equals 0, we're allowed L equals 1, and we're allowed L equals 2. So this would be the max. 3 minus 1 is 2. If L equals 2, what are my allowed M values? -2 to +2. So it would be -2, -1, 0, 1, 2. So 5 possible M values here. And so we're going to write that, but you know this. You're either going to memorize that the 4s comes before, or you're going to determine it. There are 2 ways to determine that the 4s come before the 3d, aside from memorizing it. one way is to draw the pyramid. And so the pyramid goes like this, you know. Here we separate it into different columns, like the L equals 0 column, the 1s, the 2s, and then the 2p. So L equals 1, 3s, 3p, 3d. So L equals 2. So we're okay. N equals 3, L equals 2 max. So we have L equals 0 is okay, L equals 1 is okay, L equals 2 is okay. Then we go to 4s. 4s, 4p, 4d. So we're allowed 0, 1, 2, and 3. 3 would be the max, so it would be 4f. L equals 3 is an F orbital. So S, P, D, F. And then we go 5, 5s, 5p, 5d, 5f. And then, well, if we're n equals 5, then we're allowed a max L of 4. And so what's a 4 called? L equals 4 orbital called, or subshell called. S, P, D, F, G. So we're allowed up to 5G. Let's go one more. Then we'll go 6S, 6P, 6D, 6F, 6G. What comes after that? Because now we're allowed a max of 5. So we can have L equals 0, which is a 6S, L equals 1, which is a 6P, L equals 2, which is a 6D, L equals 3, 6F, L equals 4, 6G. L equals 5 would be a 6H. So we're allowed up to 6H. And so we can see the filling order here, 1S to 2S to 2P to 3S. After the 3S comes 3P, but after the 3P doesn't come 3D. This is a common mistake. People will put 3D after 3P. What happens is the 4S come in before the 3D. So we just either memorize it. In fact, the 3D don't even go in the third shell. What shell does the 3D go into? The fourth shell. So here's the third shell. The fourth shell is going to be up here. So it's going to start off with the 400 with the 4S. 4. But now it's mixed up. You know, now we got an n equals 3 orbital in there, so things start to get mixed up. And so rather than calling it energy level, for example, the n equals 3 energy level, the n equals 3 energy level is kind of split because we have these two sub-shells or sub-levels here, and then we have the D up here. So what we'll do is we'll just call it the shell. So rather than n equals 1 energy level, I'm going to call it the first shell like I did over there, the second shell, the third shell. In the third shell, we don't have all the n equals 3 subshells. We only have the 3s and the 3p. In the fourth shell, we don't have all the n equals 4. All the n equals 4, if I look at the energy level, it's 4s, 4p, 4d, 4f. N equals 4. But here, we're going to go to 4s, and then slightly above the 4s in energy are the 5 3ds, which would be 4, 2, minus 2, a 4, 2, minus 1, a 4, 2, 0. Let's write it in here. 4, 2, minus 2, 4, 2, minus 1, 4, 2, 0, 4, 2, 1, 4, 2, 2. Takes care of the 3D subshell. And then to complete the fourth shell, we need the, after the 3D, we need the 4P here. So we'll put in 4P here. The 4P would just be a 4, 1, minus 1, 4, 1, 0, and a 4, 1, 1. And that completes the fourth shell. Yeah. So again, what I'll do is, since things get mixed up a little bit here, we've got the first shell, the second shell, third shell, the fourth shell. All right, you need to be able to draw this diagram here up through the fourth shell. there's one other way, without memorizing it, we can figure out the filling order for the orbitals. And that's from the periodic table. The periodic table, of course, is based on this quantum mechanics theory. Originally, the periodic table came from observations, experimental observations. And then later on, they correlated the periodic table with theory, quantum theory. And so here, the first period, or the first row, that's the first shell, the second shell, the third shell. Now the fourth shell, the third shell just consists of the 3s and the 3p orbitals. The fourth shell consists of the 4s, then onto the 3d, and then the 4p. Fifth shell would be 5s. So we can see it here. Fifth shell starts here, 5s. What comes after 5s? 4d. Right here. And then after the 4d comes the 5p. The sixth shell starts here with the 6s. So we start off with the 6s. And so if we look at the sixth shell, it goes 6s. What comes after 6s?
4s.
The 4f. And so we go 6s, 4f. There's not enough room to stick the 4f in here. So we took the 4f, and then the 5p, followed by the 6p. And so the sixth shell would start off with 6s, and then go to 4f, 5d, 6p. And then we start the seventh shell with 7th s, which is below here. Does it make sense? Anyway, we should be able to draw this diagram here, and then we should be able to fill it with electrons. So for example, I should be able to pick any electron in here, and you should be able to tell me the numbers. So if I pick this electron here, what are the quantum numbers for that? Each electron in copper has a unique set of quantum numbers. So what are the numbers for that electron? Did I screw this up? Do you see I screwed this up? I made a mistake. It's not 4. What is it supposed to be? 3. I screwed it up because I'm thinking n equals 4 and the fourth shell. It's actually, this set actually goes into the fourth shell. It doesn't really. And so this is not correct. It should be 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. Now it's correct. So we have that. Well, we can see it here too, you know, so 4s, it doesn't go 4s, 4d, it goes 4s, 3d. You know, 3d pop in there to the next shell. There's reason for that. The reasons you get into in Chem 1a, but not Chem 4, we're not going to get into it. And so this electron here, what is it?
3, 2, 0,
Yeah. This would be a 3, 2, 0, negative 1/2. Does everybody see that?
Wait, say that again?
3, 2, 0, negative 1/2.
3, 2, 0, I don't see that.
You know, see, the first d orbital will be a 3, 2, negative 2, 3, 2, negative 1, 3, 2, 0. And so it's in the 3, 2, 0 orbital, and it's pointed down. So 3, 2, 0, negative 1/2. That's correct. Okay. So we should be able to pick any of these. As long as we know which orbital it's in, then the first 3 should be okay, and then the last one should be easy. It's either spin up, which is plus 1/2, or spin down, which is minus 1/2. We should be able to figure it out. And so that's copper. Now, we're going to talk about one other thing here for copper, and that is the valence electron versus the core electrons here. But before that, this is not the most compact way of writing it. You know, what is the electron configuration for copper? What is the electron configuration for copper? you could write argon. There's two ways of doing it. You know, if we fill the first shell, that's helium. If we fill the second shell, that's neon. Third shell would be argon. So what we can do is we can use the argon core. That is 1s2, 2s2, 2p6, 3s2, 3p6 is equivalent to argon. So this whole thing is argon. And then we'll just add on the rest. The rest would be 4s1, 3d10. 4s1, 3d10. Now, the way we define valence electron versus core electrons. First, we look at the valence electrons. The valence electrons are the outermost electrons. They're the furthest away from the nucleus. So if there's let's say there's an oxidizer around, the oxidizer will attack the electrons that are furthest away from the nucleus first. And so which electrons are furthest away from the nucleus? Now, it becomes a little bit confusing because when I look at this, you know, let's get rid of the 4p right now. I don't have to show the 4p here because it's empty. When I look at this, it looks to me the furthest away are the 3Ds, doesn't it? Yeah, it's true. The furthest away in terms of energy, the highest energy electrons are going to be the 3D. The 4s are slightly lower in energy. But spatially, it's a different story. You know, spatially, it's because of the shapes of these things. The shape. Spatially, it looks a little different. You know, when we compare, let's compare the s. You know, if we're looking at a 1s orbital, let's say a 1s orbital is this big. How much bigger is a 2s orbital? Well, it turns out, based on the math, a 2s orbital is about 4 times bigger than a 1s orbital. You know, it's just more energy. Energetic. A 3s orbital is about 9 times bigger than a 1s orbital. That would be a 3s orbital. And so if we look at the 3s orbitals like this, if we look at a 3d orbital, 3d orbitals are around the same scale, you know, like this. However, when we go to a 4s orbital is about, turns out to be about 16 times bigger than a 1s orbital. So 4s orbital is huge. So even though the 3d orbital is higher in energy, the 4s are just further out from the nucleus, or have a probability of being further out from the nucleus. Greater probability. And so the way we define valence electrons is they're the outermost. The outermost are going to be the highest N. Highest N electrons. Well, the highest N is going to be N equals 4. And so we have 2 different ways of doing this. We have the filling order. The filling order is going to be argon, 4s1, 3d10. And then we have the losing or vacating or removing order. So when we remove these, in other words, let's say you're an oxidizer. An oxidizer comes along. The oxidizer is going to want to take the easiest electron it can take. The easiest electron that it can take is the one furthest out from the nucleus, the one that's closest to the oxidizer. When we look at it, well, in terms of energy, the 4s is closer. In terms of distance, the 4s is farther. This is, the distance is a little funny because of the shapes, the different shapes of these things. And so we have 3d10 like this, and then 4s1 like this. And so if you're an oxidizer, you're going to attack the 4s1 electron first. If I attack the 4s electron, let's say I remove the 4s electron, then what is the charge? If copper loses 1 electron, what's its charge? Plus 1. So plus 1 is a common charge for copper. It's not the most common charge for copper. The most common charge would be plus 2, but there's a reason for that. And so the way we define the core is, yes, we have the argon core, the filled shell. On top of the argon core, we have the filled subshell, the 3D. Now, filled subshell, the 3D10 is stable, except for copper, which can lose 1 of them, so it takes 1 slice out. Then we have the valence electrons. Here, the valence electrons would be the highest. And so copper technically only has 1 valence electron. But if you're an oxidizer, you might be able to attack this 3D, which is not part of a filled shell. It's a filled subshell. Filled shells are more stable than filled subshells. And so we're going to look at some other species next. For valence and zinc. Okay, when we go to zinc, the electron configuration for zinc is going to be argon, 4s2, 3d10. So zinc just adds 1 more electron on top of copper, and so where's that electron going to go? The electron's going to go in 4s complete that. So 4s2, 3d10. Now, how many valence electrons does zinc have? 2. Zinc has 2 valence electrons. And so this is the filling order. We could rearrange this. And when we rearrange this, we go in numerical order. So it'll go 3 comes before 4. So it would be 3d10, 4s, 2. And so zinc has 2 valence electrons, and the rest are core, or inner shell electrons. These will be core. Do you know how many electrons zinc likes to lose? 2. Zinc 2 plus, it's fixed charged, and so it's just plus 2. And so that's why these, if you look at these elements here, these elements are called the pseudo group 1. It's pseudo group 1 because it has actually 1 valence electron, and this is pseudo group 2 because it has 2 valence electrons. These are the real group 1. The real group 1 and the real group 2. So let's take a look at the real group 1 and the real group 2 rather than the pseudo group 1 and the pseudo group 2. So looking at the hydrogen, how many valence electrons does hydrogen have? 1. It's just a 1 shell. It's partially filled. If we go to lithium, lithium has the first shell filled, so it would be helium, 1s2. And then the second shell is partially filled, it's 2s1. So how many valence electrons does lithium have? 1. Sodium has the neon core, first shell, second shell filled, and then the third shell is partially filled. The third shell just has 1 electron. How many valence electrons does sodium have? 1. Potassium? 1. All these have 1 valence electron. So if you're an oxidizer, you're going to come and take that electron, the one that's furthest from the nucleus. So if I'm going to attack potassium, I'm going to take this 1 4s electron here, remove it. I'll also try to take the core electron. So I want more electrons. So I'll take 1 electron, but this is filled shells. Filled shells are stable, so it's very difficult to take a core electron. And so if you're an oxidizer, you're probably going to be able to take off the 4s1, but probably not going to be able to break up the core, or the filled shells.
if the oxidizer was to remove the one from the potassium, would it then be changed back to neon?
No.
No? It
No.
would stay argon?
Yeah, in a way it does, in a way, but it doesn't. So, for example, if potassium, okay, loses that, and so if we look at potassium, potassium's got the first shell filled, and the second shell is filled. And the third shell is filled. And then the fourth shell just has one electron here, 4s1. This is potassium. If potassium loses that electron, then we're left with the outermost shell. Now it's going to be the third shell, it's completely filled, 3s and 3p, which makes it stable. Nothing happens to these, the core electrons. So a filled shell is very stable, so it's going to stay like this, and that's going to make potassium ions. Are potassium ions very reactive, or are they pretty stable? Potassium ions are pretty stable. You know, they're not really reactive. They're extremely poor oxidizers. In fact, the second worst oxidizer on the chart. And so, so in a sense, that it becomes a lot less reactive. Neon's, argon's not very reactive. Well, so this is group 1. It's group 1 because it has one valence electron. And one valence electron is susceptible to attack by oxidizers. If we go to group 2, how many valence electrons does group 2 have? Group 2, well, they all have 2 valence electrons. Those 2 valence electrons can be attacked. Therefore, group 2 are going to form +2 cations. Group 1 forms +1 ions. Now we have group 3 with the main group over here. When we go to group 3, how many valence electrons does group 3 have? 3. And so here, the 1s is core, and then we have neon core. But if we look at the outermost electrons, we have 2s2, 2p1, all the other 3. So if you're an oxidizer, you're going to attack these 3 electrons and make a +3 cation. Like aluminum. Aluminum's fixed charge. Its fixed charge is going to be +3. The valence electrons get lost, leaving us with a neon core. This is going to be unreactive, and we'll have aluminum 3+. Let's go down to gallium. If we go down to gallium, how many valence electrons do we have? Well, if we look at the fourth shell is not full. The fourth shell is going to have 4s2, 3d10, 4p1. So, if we go to gallium, we have 4s2, so there's 2 electrons here, all the way up to the third shell is filled. So that's stable. We got 4s2, 3d10, 4p1. How many valence electrons are there?
11?
Yeah, if you look in the fourth shell, there are a total of 11 electrons in the fourth shell. Two, actually more than 11. There's 2 plus 10 plus 1, 13. We have 13 electrons in the fourth shell. And so does that mean there are 13 valence electrons? No, it doesn't. It doesn't. And so one thing we could do for gallium is we can rewrite the electron configuration. The filling order is like this. It goes argon, 4s2, 3d10, 4p1. What we're going to do is we're going to rearrange them. And so we're going to get the, the attack or the leading or the moving order. And so we're just going to do a numerical. It's going to go 3, and then 4. We'll go 4s2, 4p, 1. And so the highest end are the valence. So the highest end is 4. So when I look at the highest end, n equals 4. How many electrons are there? 3 electrons. And the rest are going to be core. And so we have 3 electrons valence, the rest are core. And so the core electron will be our standard argon core plus the 3d10 subshell. The 3d10 subshell is a filled subshell. It's not as stable as a filled shell. However, there is stability in that filled subshell. And so something like gallium will have 3 valence electrons because the 3d10 will now be part of the core electrons or the inner electrons. So we'll just call these the inner electrons, core, the 3d10. Because it's a filled subshell, if you're an oxidizer, you're going to attack the 4p first and then the 4s, so plus 3 is possible. How about carbon? How many valence electrons in carbon? 4. In silicon? 4. In germanium? 4. That's because the 3D are going to be part of the core. Nitrogen? 5. Neon? 5. Arsenic? 5 as well. 3D. Oxygen? 6. Sulfur? Selenium? 6. 3D absorbed in there. So, over on the left, it's easier to lose electrons. Over on the right, what we can do is we're very close to filling up the 4th shell. Like for example, here in krypton, we fill up the whole 4th shell. The 4s2, 3d10, 4p6, it's filled. So the 4th shell is filled. Bromine is just 1 electron short. And so bromine would much rather gain an electron to fill up the 4th shell than lose electrons. Same thing with selenium, arsenic. And so things on the right tend to gain electrons in order to fill up that remaining shell, the valence shell. Things on the left tend to lose electrons. Let's take a look at the, those are the A's. Let's look at the B group. The B group is, so we go from 2A to 3B. We go from 2A to 3B, or group 3 here. How many valence electrons are here? 2. There are 2 valence electrons. So a common charge would be plus 2, because if an oxidizer comes here, the first electrons that are going to go are the 4s electrons. The oxidizers can take those, leaving scandium plus 2. But there's a difference between the other Ds. Like when we're looking at the other Ds, those are D10. D10 is a filled subshell. This is a D1. That means there's only 1 electron there. And so it doesn't have the same stability as a filled or half-filled subshell. So what happens here is the oxidizer could attack, once it's gotten the valence, it could start attacking the core. Now this core electron is very different from this core. This core, filled shell. This core is a partially filled subshell. And so if you're an oxidizer, there's potential for attacking this core after you've gotten rid. And so plus 2 is common, and if it takes one of these, it'll be plus 3. And so for scandium, and in fact, this D1 is easy to take, so scandium is always plus 3. Scandium's fixed charge, plus 3. Titanium's variable charge. Do you know what the charges on titanium are? Plus 2 is 1. Yeah, plus 3, plus 4. So it could lose all 4. What about plus 5? No, plus 5 not, because then we'd have to start attacking the argon core. It'd be difficult. Vanadium? Vanadium plus 2, plus 3, plus 4, plus 5. So vanadium between plus 2 and plus 5 are common. Chromium. Yeah, chromium will go up to +6. Manganese will go up to +7. Iron should go up to +8, but it's very hard to lose 8. Very hard. You saw, with manganese and chromium and +6, they become extremely reactive. So it's difficult to go to +8. And so when we look at the periodic table and look at the these are the max. For example, scandium is 3B, titanium is 4B, vanadium is 5. This is max charge. Chromium is 6, manganese is 7. Iron, cobalt, nickel are 8. And it's very rare that you're going to see these in +8 ever. Iron, what's much more common for iron? If we look at the electron configuration for iron, it makes sense. Iron is going to be argon, 4s2. So argon has how many electrons? 18 electrons. Iron has how many electrons? 26 electrons. And so we got 18. And then 19, 20. And then we go to 4s to what? 3d. 21, 22, 23, 24, 25, 26. So iron, if it loses the 2 valence electrons, it's going to be iron +2. If it loses one of the d electrons, it will become iron +3. If it loses one of the d electrons, then what are we left with? We're left with a half-filled d subshell, which has got some additional stability. And so it makes sense to stop there. That iron +2 and iron +3. Iron +4 would break that half-filled symmetry here. So we'll leave it. And so we can start correlating some of the properties of these species with the theory here, quantum. It's quantum mechanics. Well, here we're talking about the core. Okay, these are the 2 exceptions you need to memorize, chromium and copper. The book has a different method for determining electron configuration. So we write the electron configuration for chlorine. The book doesn't ask you to write energy level diagrams. Because energy level diagrams take up a lot of space. So instead, they'll ask you to write the electron configurations, but I will ask you both. And so if we were to write for chlorine, the energy level diagram would be 1s, we've got 2 electrons there. Chlorine has a total of how many electrons? 17 electrons. So that's 2 electrons, and then 2s, another 2, and then 2p will have 6 electrons in there. So that takes us to 10 electrons. Then 3s, 12 electrons, and then 3p, 13, 14, 15, 16, 17. So when we go there, this will be the electron configuration. If you look at it, it's just 1 electron short of filling that 3rd shell. When we do the electron configuration, it would be 1s with 2, 2s, 2, 2p subshell is 6, 3s subshell is 2, 3p subshell is 5. If we use the core, noble gas core abbreviation, it would be neon 3s2, 3p5. And so you can see why chlorine would be an oxidizer. Chlorine wouldn't want to lose electrons. If it loses electrons, it'd have to lose way too many electrons. How many electrons would it have to lose? So either it's going to vacate the third shell or fill the third shell. If it fills the third shell, it's going to gain 1 electron. If it vacates the third shell, it's going to lose how many electrons? 7 electrons. 7. And so chlorine's oxidation state ranges from -1 to +7. So it can happen. For example, we see chlorine gain an electron to form chloride. And so that means an electron is going to fill that. It took the electron from something. But we can also see that chlorine can lose electrons if there's something more powerful around, like in this, perchlorate. You know, what's the charge on chlorine, the oxidation state on chlorine in perchlorate? +7. And so here, we got +7 on chlorine. That's perchlorate. How about this? Perchlorate. Let's throw in another oxygen in there. If I throw in another oxygen in there, I'll make something like hyperchlorate or perchlorate, or come up with a new name for this. What would chlorine be here? It would be, yeah, it would be +9, which means it would have to lose, in addition to the valence, it would also have to lose 2 chlor. Is that going to happen? No, it would cost way too much energy to take one of these filled shell electrons, so it just isn't going to happen. So this is what we end up with here. We're going to end up with neon, 3s2, 3p5. Just 1 electron short with filling that. I don't know what the book is doing here. 2 + 2 + 6. The way I usually remember it is like this. Helium has 2 electrons. Neon has, argon has 18. So we just do it that way. There's one other thing to keep in mind. And let me show you what that one other thing is. Back here. All these have filled valence, the noble gases, so they're pretty unreactive. All these are 1 electron short. And when we fill the valence, how many electrons does it take to fill the valence? Well, it takes 1, there's usually no electrons here, this is already filled. The filled valence means that there are how many electrons? 8. And so here there's 7, so we need to get to 8. Here there's 6, we need to get to 8 to fill it. And so 8 is a special number here. If you look at all these have 8 valence except for helium. Helium is 2. Helium needs what they call a duet. These need an octet of electrons. 8 need an octet. And so octet is a special number. Octet just means we've filled this, the S and the P. And so, let's see. So these numbers I look at a little differently than the book does here. I go in patterns like this: 2 to 10 to 18. You know, in this case, they're doing it by individual cell levels. All right, let's take a break and then we'll continue this.